Well, I'm Dave Smith. I am the co-chair of the Angler Survey Committee, but also I'm a PhD student at LSU, and my dissertation work is all surrounded around working to innovate and optimize creel survey design and estimation. But this project here is actually one that I started while I was a biologist with Texas Parks and Wildlife. And I've continued to work to put this manuscript out and submit this research with other TPWD biologists, as well as Mike Allen at University of Florida. So before I jump into my talk, I'd like to make a few acknowledgments. There's been several colleagues at LSU that have really helped shape this research as we've finalized the models. But I want to give a shout out to Matt Zink. He really helped put my model together and really provided a lot of insight on the age-structured model building. There's been too many biologists and technicians at Texas Parks and Wildlife to list that have collected data and been a part of designing the research objectives of this project, but listed here are some of the scientists that really had a hand in shaping this project. And the funding source for a lot of the creel surveys, for the majority of the creel surveys run on this project, came from sport fish restoration funds. So understanding how angling sonar has evolved over time can give us a glimpse at just how far the technology has come recently, going all the way back to the beginning of angling sonar in 1957 with devices known as flashers. These were a dial of flashing lights that anglers could look at and tell what was underneath their boat. In the early 70s, the next innovation angling sonar came along with paper graphs, which were devices that need to be continuously fed with carbon paper, and a stylus drew bottom contours on these graphs. In the mid 80s, digital display screens finally came on the scene, but as you can see here, the resolution in these early devices was really poor. In fact, paper graphs were preferred over those early digital display screens for a long time. But when we look at what anglers are looking at today, the early devices really pale in comparison when we're thinking about downscan and side scan sonar, which was introduced in the late 2000s. With this, anglers could get extremely accurate views of what underwater environments look like at a level that wasn't available with previous iterations of angling sonar. And that leads us to the most recent innovations with live imaging sonar. You're probably familiar with Garmin LiveScope, which was effectively introduced to the market in 2018. Now there's several other competitors on the market, including Active Target and I think there is another. There's definitely a few live imaging sonar devices in the market, but Garmin LiveScope is the most popular. And with live imaging sonar, anglers have the ability to pinpoint individual fish locations and watch as that fish reacts to the presence of bait or lures in ways that you couldn't do previously with scanning sonar or any of these other iterations of angling sonar. At least not with the level of precision you can with a live imaging sonar. And as catch and harvest efficiencies presumptively improved with live imaging sonar, we've seen angler concerns voiced by news sources in Tennessee, in Kansas, and even in my former home state of Texas. And if you do a simple browser search of LiveScope concerns, it's definitely going to take you down a deep rabbit hole, but you don't have to search very hard to find anglers voicing their concerns surrounding live imaging sonar, particularly when it comes to crappie fisheries. Now, with the context that anglers were concerned about the impact of live imaging sonar, we wanted to conduct a baseline evaluation, see what live imaging sonar currently looks like on reservoirs, on some of the more popular crappie reservoirs in Texas. With that, we added a live imaging sonar question to our creel surveys. We conducted creel surveys on three major crappie fisheries. That includes Lake Fork, Lake of the Pines, and Sam Rayburn Reservoir. And during those creel surveys, we asked traditional questions to produce estimates of effort, catch, and harvest. But we also asked, did you use live imaging sonar during your fishing trip? And that allowed us to subset into live imaging sonar users and live imaging sonar non-users, which includes anglers that didn't use any electronics during their fishing trip, or anglers that used more traditional angling sonar or downscan or side scan sonar without the use of live imaging sonar. So shown here is our directed crappie effort estimates for each of the lakes, as well as an aggregate average. And we saw live imaging sonar utilization either reaching or exceeding a majority of directed crappie effort on each of these reservoirs, with users shown in blue here and non-users effort shown in purple here. It's ultimately led to an aggregate average of 57%. 57% of the effort we observed on these three reservoirs came from live imaging sonar users. We also wanted to look at what catch efficiencies looked like between the two groups. We compared catch per hour and harvest per hour, and we saw catch rates improved in efficiency by 24% when comparing users to non-users. But more importantly, when we think about effects on ultimately on fishing mortality, we saw an even higher increase in harvest rate, with harvest efficiency increasing by 31% when comparing users and non-users. Ultimately, we want to do a side-by-side comparison of users and non-users. So we took those harvest rates and multiplied it by an equal scaling factor to ultimately give us a proportional harvest when comparing users and non-users. We then used this estimate later on in our age-structured models when we assessed what potential effects on exploitation might look like. So the results of our creel survey show that crappie anglers in Texas frequently utilize live imaging sonar, and the anglers that are using live imaging sonar are harvesting crappie at significantly higher rates than the non-users. We want to take things one step further and estimate population level effects relative to this increased crappie harvest. And the way we did that is through simulating an age-structured model with potential exploitation rates, which we derived from the harvest differences between users and non-users. So ideally, we would have known what fishing mortality looked like before the implementation of live imaging sonar. Unfortunately, that data is not available. So we based our initial estimates of fishing mortality on three surrogate levels, roughly based on a meta-analysis conducted by Allen and Miranda that combined 18 different crappie exploitation studies, and we ranged it from low to 20% to high fishing mortality of 50%. Now that sounds really high, but crappie fisheries are extremely harvest oriented, and the mean from that meta-analysis was a fishing mortality of 48%. So we've seen evidence of fishing mortality estimates reaching for crappie fisheries reaching a lot higher than 50%, which puts these in perspective as conservative measures of fishing mortality. We then estimated what inflated mortality might look like using those those different harvest rates, and this has the potential to increase fishing mortality from 3% at the low end to 7% at the high end. We then built our age structured model following a traditional stock assessment approach, where in year one, you have your unfished population, where you start with a scaling factor. For us, we used 10,000 fish. It's an arbitrary number, but this the number of fish in each subsequent age class declines by a constant rate of natural mortality. In the next years, we start to plug in fishing mortality. So now fish are taken out of each age class, both by natural mortality and fishing mortality. We simulated recruitment in the number of age one crappie following a log normal distribution with a mean of 0 and a coefficient variation of 0.8 to mimic the really high recruitment variability we typically see in crappie fisheries. We then can plug in growth and maturity estimates to give us our estimate of the total eggs produced by a population in a given year, or a measure of fecundity. We can then take the measure of fecundity in a given year, divided by what fecundity would be in the unfished virgin population, and that gives us a reference point for overfishing and spawning potential ratio, or SPR, which is really commonly used in stock assessment. So shown here are simulations. They're violin plots representing the 10,000 simulations under each exploitation scenario, with the violin plots to the left showing non-user exploitation. This is the exploitation that we estimated before the implementation of live imaging sonar. And then next to it, we show the response to inflated exploitation. This is what we hypothetically estimated exploitation might increase relative to the use of live imaging sonar. And we did this for fast-growing crappie populations, which we typically see in Texas. We also did this for moderately growing crappie populations, which might be more reflective of general crappie populations across the US. We set our reference point for recruitment overfishing at an SPR of 30%. We borrowed this from another age-structured modeling paper surrounding crappie populations in Florida. And as you can see, even at the highest levels of exploitation, we don't have simulations reaching below our estimate of recruitment overfishing. And in fact, we upped exploitation all the way up to 80% to see what the response might look like. And we still had SPR values for both fast growth and moderate growth above our threshold for recruitment overfishing, indicating that the potential for recruitment overfishing within the parameters that we set up for our age structured model, the potential is pretty low. We also wanted to look at yield per recruit to see if we could see any estimates to estimate the potential effects of growth overfishing. And you can see at the highest levels of exploitation, median yield per recruit continues to increase, which shows us that we haven't yet reached the maximum of yield per recruit, which once we start to see estimates of yield per recruit start to decline relative to exploitation, that's when we start to identify growth overfishing. So the potential for growth overfishing was also low, with exploitation up to 57%. This isn't to say that we're not going to see any potential effects on the crappie populations relative to increased fishing mortality. Shown here is the proportion of memorable size crappie, or 12-inch crappie, And you can see that as you increase exploitation, you do see an effect on the population in the proportion of memorable sized fish, which can really affect angler satisfaction. And it is important to understand as we think about how populations might change with potential increases in fishing mortality. So the results of our study showed that the overfishing potential for crappie, given the estimates of maturity that we plugged into our stock assessment models, with exploitation up to 80, as high as 80%, we didn't see evidence of recruitment overfishing with SPR levels below 30%, which shows us that crappie are really they're really hardy species with fast growth rates and a very small size, its sexual maturity, and to overfish a typical crappie population, it takes a lot more exploitation in the models we ran than the exploitation, the levels that we applied in this model. So to conclude, live imaging sonar users are harvesting crappie at significantly higher rates than the non-users. The overfishing potential in our simulations was low, but it's important to note that this is all relative to a 10-inch minimum length limit, which shows that this is a pretty effective tool at minimizing recruitment and growth overfishing. However, when we run simulations without this 10-inch minimum length limit, it really changes the output of the age structured model. So it's important to put all these in context of that regulation and understand that we're going to observe different things where there might not be a minimum length limit, or there might be a 9-inch or 8-inch minimum length limit. And ultimately, more precise estimates are needed to truly assess the impact of live imaging sonar. We simply observed that users were harvesting more fish than non-users, but we don't know if those users were always harvesting fish at those rates without understanding how their fishing has changed relative to live imaging sonar. And ultimately, we don't know what fishing mortality is at on any of these reservoirs. So to truly understand whether the overfishing potential exists on a fishery, we're really going to have to get precise reservoir specific estimates of exploitation, and that's typically done through tagging studies. That concludes my talk. I appreciate y'all tuning in, and with that, I can take any questions. Got a question from Nick. We're not really sure about the adoption rate. For this live imaging sonar question in Texas Parks and Wildlife is only been added to creel surveys since I think in 2021 is when we started adding that to the creel surveys. So it's hard to tell what the adoption rate is, but it seems with it being introduced in 2018 and a creel survey, those creel surveys were conducted in 2022 and 2023, and we're seeing the majority of crappie anglers using it. The adoption rate, it seems to be pretty high. John, go ahead.
Yeah, thanks, Dave. This is super cool work you guys are doing. Kind of similar to the next question. You said that this is kind of a unique rate for this lake and fishery, and Is it sort of across all anglers or pretty specific to crappie? Because I'm from Minnesota and we're working on this as well. And we have, based on preliminary takes from the last few years of surveys where we asked, we had a much, much lower use rate, like much like in the 10 to 12% of our most of the ice anglers. But so this is pretty kind of eye-opening for me. Do you think this is representative of other fisheries and systems across Texas?
So we also conducted these creel surveys. We did this study on 10 different reservoirs that we had just the TPWD had their traditional creel survey set up on. And the amount of effort that goes into targeting crappie on some of those other Texas reservoirs, it's not as high. Largemouth bass is the primary focus of anglers in Texas. So, but going to those reservoirs that I highlighted, those are reservoirs where we've seen up to 30% of total effort geared towards crappie in historic creel surveys. So I think that our findings are relative to other reservoirs and throughout the southeast, and I'm not really sure what it looks like in other fisheries, but definitely wherever crappie is a focus, that's where we've seen higher adoption rates. Yeah, Daniel.
I just wanted to make a comment, kind of follow up on that. Like we started asking here in Florida too, and it, just based on our water bodies, we're shallow, not a lot of depth like you have in some of the reservoirs. And even though we do have high crappie effort, we just don't tend to have some of the offshore structure and drop-offs where we just haven't seen the anglers implement this technology as readily because it just doesn't seem to benefit them in some of those scenarios where maybe they're going through a single trough, just trolling small plugs or minnows or what it might be. But we just don't have that offshore habitat. So depending on the system that maybe you're managing and what part of the country you're in, you might see anglers that may utilize this more just based on those systems and the habitat that the crappie might be using. So it like John said, we just haven't seen that high of a percentage of crappie anglers using it, but we think it's likely just due to how they fish here in Florida and not having those big deep drop-offs and offshore habitat available.
Mm-hmm. Yeah, it's definitely system specific. In fact, so what I showed was the aggregate catch rates, but when you look at the variability from reservoir to reservoir, there's actually we saw in Lake Fork, we saw a big a much larger difference between users and non-users. And then compare that to Sam Rayburn, we actually saw non-significant differences between users and non-users on that lake. But in the aggregate, that's where we observed the significant differences. So just like in any sort of stock assessment, you're doing a simplification of something that's a lot more complex and going to be system specific. But here we're just trying to get an expected average response to increase fishing mortality. Craig, go ahead.
Yeah, hey Dave. Yeah, thanks for the talk, and thanks actually for the whole session on database and everything. So very useful. I put a question in the chat, but I thought I'd just kind of bring it up. Do you have any insight on how this technology is being used to target individual fish? And I'm thinking like alligator gar, maybe catfish. I've heard in Oklahoma down, snagging paddlefish that they're actually targeting individuals just swimming around the lake to find. So not sure if you're aware of that with any other kind of larger fish like, say, alligator gar or catfish.
Yeah, so I think that there's probably there's probably 3 or 4 papers in this study that that I just don't have time to analyze all the data, but we got it with every species that was targeted, and so we have live scope data for bass, for catfish, for all those species. We in Texas, the bass anglers and the crappie anglers are the ones using live imaging sonar. Bass anglers have adopted it at rates that are not as high as the crappie anglers, but still pretty high. On some reservoirs, it's over a majority of it. Bass anglers are using the technology, and I think some folks at Texas Parks and Wildlife are really interested at looking at some of those responses as well. But with crappie, we saw increased harvest rates that might potentially affect the fishery related to that. And we didn't see those increased harvest rates with those other species. So all that to say is there's still a lot to unpack and go through with this data. And I think that there are some interesting questions like that, especially with gar and paddlefish and catfish. And as far as catfish go, I'd point you to the Ben Neely paper that was recently published, where they did they've done a similar approach with both crappie and blue cat. I think it was blue catfish with live imaging sonar. So there's definitely a lot more interesting research questions to unpack here. But yeah, I appreciate everyone tuning in, and